Good morning. Applications of congruences include hashing, pseudorandom numbers, and check digits, among other applications. Hashing functions. Hashing is a mechanism that allows the rapid lookup of a key value. Hashing trades space for time. A simple calculation is performed on a key, often in character form, to produce an index of a record containing data associated with the key. One of the most common hashing functions is h of k is equal to k mod m, where k is the key and m is a prime number representing the number of locations available for storing records associated with the key. Example 1.1. Find the memory location assigned by the hashing function h of k equal k mod 111 to the record of a customer having a social security number of 064212848. So when we hash the social security number, what we get is 14. Example 2. Find the memory location assigned by the hashing function h of k equal k mod 111 to the record with social security number 037149212. And what we get here is 65. Example 2. After making the assignments of records to memory locations in example 1, assign memory location to the record of the customer with social security 107405732. First note that the hashing function h of k, k mod 111 yields 14. However, this location is already occupied by the record of the customer with social security number 064212848. But because memory location 15, the first location following memory location 14, is free, we assign the record of the customer location with the customer with social security number 107457723 to this location. In example 1, we used a linear probing function, namely h of k comma I, where h of k plus I mod m to look up the first three memory locations where I runs from 0 to m minus 1. Pseudorandom numbers. Randomly chosen numbers are often needed for computer simulations. Different methods have been devised for generating numbers that have properties of randomly chosen numbers. Because numbers generated by systematic methods are not truly random, they are called pseudorandom numbers. The most commonly used procedure for generating pseudorandom numbers is the linear congruential method. We choose four integers, the modulus m, the multiplier a, the increment c, and the seed x sub naught, with 2 less than or equal to a less than m, 0 less than or equal to c less than m, and 0 less than or equal to x sub naught less than m. We generate a sequence of pseudorandom numbers x sub n with 0 less than or equal to x sub n less than m for all n by successively using the recursively defined function x sub n plus 1 is equal to the quantity a x sub n plus c mod m. It is possible to generate a uniform distribution having the values between 0 and 1 by dividing the values of the sequence x sub n by m, the maximum value, and the modulus. Example 3. Find a sequence of pseudorandom numbers generated by the linear congruential method with modulus m equal 9, multiplier a equal 7, increment c equal 4, and seed x sub naught equal to 3. We compute the terms of the sequence by successively using the recursively defined function x sub n plus 1 is the quantity 7x sub n plus 4 mod 9 by inserting the seed x sub 0 equal 3 to find x sub 1. We find that x sub 1 is equal to 7, x sub 2 equal 8, x sub 3 equals 6, x sub 4 equal 1, x sub 5 equal 2, x sub 6 equal 0, x sub 7 equal 4, x sub 8 equal 5, and x sub 9 equal 3, and we repeat that sequence forever. Because x sub 9 equal x sub naught, and because each term depends only on the previous term, we see that the sequence 37612045378612045 is generated. This sequence contains 9 different numbers before repeating. Check digits. Congruencies are used to check for errors in digit strings. A common technique for detecting errors in such strings is to add an extra digit at the end of the string. The final digit or check digit is calculated using a particular function. Then, to determine whether a digit string is correct, a check is made to see whether this final digit has the correct value. We begin with an application of this idea for checking the correctness of bit strings. Example 4, parity check bits. Digital information is represented by a bit string split into blocks of a specific size. Before each block is stored or transmitted, an extra bit called a parity check bit can be appended to each block. The parity check bit x sub n plus 1 for the bit string x sub 1 through x sub n is defined by x sub n plus 1 is equal to the sum of x1 through xn modulo 2. It follows that x sub n plus 1 is 0 if there's an even number of 1 bits in the block of n bits, and it is 1 if there are an odd number of 1 bits in the block. When we examine the string that includes parity check bit, we know that there is an error if the parity check bit is wrong. However, when the parity check bit is correct, there still may be an error. A parity check can detect an odd number of errors in the previous bits, but not an even number of errors. Suppose we received a transmission. Suppose we received in a transmission the bit strings 0110, 0101, and 1101, 0110, each ending with a parity check bit. Should we accept these bit strings as correct? Solution. Before accepting these strings as correct, we examine their parity checkbooks bits. The parity check bit of the first string is 1 because 0 plus 1 plus 1 plus 0 plus 0 plus 1 plus 0 is congruent to 1 modulo 2. The parity check bit is correct. The parity check bit of the second string is 0. We find that 1 plus 1 plus 0 plus 1 plus 0 plus 1 plus 1 is congruent to 1 modulo 2, so the parity check bit is incorrect. We conclude that the first string may have been transmitted correctly, but we know for certain that the second string was transmitted incorrectly. We accept the first string as correct, even though it still may contain an even number of errors, but we reject the second string. Example 5, Universal Product Code, UPCs. Retail products are identified by their universal product codes. The most common form of a universal product code has 12 decimal digits. The first digit identifies the product category. The next 5 digits identify the manufacturer. The following 5 identify the particular product, and the last digit is a check digit. The check digit is determined by the congruence 3x subscript 1 plus x2 plus 3x3 plus x4 plus 3x5 plus x6 plus 3x7 plus x8 plus 3x9 plus x10 plus 3x11 plus x12 is congruent to 0 modulo 10. Answer these questions. Suppose the first 11 digits of a UPC are 793573434104. What is the check digit? And B, is 041331021641 a valid universal product code? Part A. Solution. We insert the digits 79357343104 into the congruence for the UPC as I have done in the table below. When all is said and done, we have 98 plus x subscript 12 is congruent to 0 modulo 10. Hence, x sub x12 is equal to 2 modulo 10, making the check digit 2. For part B, to check whether 04133-102-1641 is valid, we insert the digits into the congruence these digits must satisfy. we have 44 is not congruent to 4 modulo 10, and hence 04133 102 1641 is not a valid universal product code. Example 6. ISBNs. All books are identified by an International Standard Book Number, ISBN-10, a 10-digit code X1 through X10 assigned by the publisher. More recently, we have an ISBN-13, which has 13 digits. An ISBN-10 consists of blocks identifying the language, the publisher, the number assigned to the book by its publishing company, and finally a check digit that is either a digit or the letter X used to represent 10. This check digit is selected so that X10 is the sum from I equal 1 to 9 of I times X subscript I modulo 11. Or equivalently so that the sum from I equal 1 to 10 of I X subscript I is congruent to 0 modulo 11. Answer these questions about ISB 10s. The first 9 digits of an ISB 10 of the 6th edition of this book are 007288008. What is the check digit? And part B is 084930149X a valid ISBN 10? So for part A, we insert the digits of 007288008 into the congruence for the ISBN 10 check digits to form the congruence equation. And what we get is X10 is congruent to 189, is congruent to 2 mod 11. Solving the congruence equation, we find that X10 is equal to 2. Solution, part B, we insert the digits 084930149X into the congruence for the ISBN check digits to determine if this congruence is satisfied, and using this table. And what we find is that it's 2 mod 11, and 2 mod 11 is not congruent to 0 mod 11. Hence, 084930149X is not a valid ISBN-10 number.